This is Alan Turing's paper from 1950, Computing Machinery and Intelligence. Before getting into the paper, I'll say a little bit about the context of this paper. Alan Turing is, I believe, one of the most influential humans of the 20th century. In his doctoral work in 1936, he wrote a paper on computable numbers, where he introduced the idea of what is now called a Turing machine. This is the first abstract idea of a general purpose computer that anyone has had. Although there were ideas in earlier centuries, people like Gottfried Leibniz had proposed the idea of a computing machine, and Charles Babbage in the early 19th century actually built one, which Ada Lovelace showed how to program. But Turing's machine, even though he didn't build it at the time, was the first one that could be shown to be truly universal. Any computational task that any machine can conceivably solve can be described by a sequence of instructions that the Turing machine can follow and then implement. That is, he invented the idea of programming a computer and the idea that one computer could solve any problem if you just write the right program. Another equally important point that he makes in this paper, though, is that although this machine is universal and can solve any problem that a machine can solve, he also showed that there are problems that this machine can't solve, and therefore that these problems can't be solved by any sort of machine. In particular, one of these problems is the problem of determining whether or not a particular computation will ever halt. The fact that this is unsolvable is why, no matter how far computers advance, we always occasionally end up with a program that crashes the computer. There's no way for the computer to predict whether or not that's going to happen and prevent it from happening. I'll put a link in the description to the Wikipedia article about Turing machines. Now, this work about the general purpose computational machine would already make him one of the most influential people of the 20th century. But additionally, during World War II, the British government set up a secret research station in Bletchley Park, where they gathered people to work on breaking the German codes. There was a particular coding device called the Enigma machine that they knew that the German U-boats were using to communicate with the bases. They had information from the Polish spy service on how this machine worked, and the Polish spy service had even built some machines, some mechanical devices that could quickly check many different settings of the Enigma machine. But there were so many settings that this was very slow, and you needed to use a lot of educated guesswork to manage to break the codes in a usable amount of time. And during the war, Alan Turing and I.J. Good and various other people helped develop important statistical techniques to speed up this process, which ended up being not just influential in ending the war sooner, but also in the post-war development of Bayesian statistical analysis in the sciences. Additionally, during the war, they discovered that there was a separate code system that wasn't the Enigma machine, the Lorentz cipher, that was being used by Hitler to communicate directly with his generals. This cipher was too hard for even these existing mechanical devices to crack, and so Turing, together with a larger team, built an electronic computing machine called the Colossus to break this code. And they were able to eventually break it and discover many of Hitler's secret plans. And after the war, the existence of this Colossus machine was kept secret, but it was the first electronic computer that was ever built in the entire world. Much of the team that had worked on it, including Alan Turing, then after the war moved to the University of Manchester, where they also built one of the first publicly acknowledged electronic computers. And so in 1950, at the time that this paper was published, Alan Turing had been working on electronic computers for many years and probably had a better sense of their capacities and limitations than anyone else in the world. And that's why in 1950, he was already thinking about this question. Can a machine think? Can computers be intelligent? And so this paper is probably the one thing by Alan Turing that is most widely known by the general public. In this paper, he introduces what we call now the Turing test to determine whether or not a machine can think. And importantly, he suggests he's actually just ignoring the question, can a machine think, and replacing it by a more practical and meaningful question. And the question of whether this is an appropriate replacement of the question turns out to be one of the central questions of cognitive science in the late 20th century. Now note, this paper was published in 1950. At this point, there were several electronic computers in the world. There was one in Manchester, there was one in Princeton, there were probably a couple others, but it was a single-digit number of computers. These computers were all operating on vacuum tubes. The transistor was only invented in 1948, and they didn't invent a silicon transistor until 1954, just a few months before Alan Turing died. And yet already in 1950, he was predicting the course of the development of computing technology all the way out until the end of the 20th century. As we'll see when we get to those parts of the paper, his predictions, while they weren't precisely on target, were remarkably accurate. And importantly, he didn't just forecast the growth in power and prevalence of computers, but also many of the important central debates in artificial intelligence. Is it better to program a machine to work with symbols, like the original Turing machine, or to imitate the neural networks of a brain? Will it be better to try to program an information by giving it information about the world, or is it better to give the machine a capacity for learning, like a human child, where it can eventually develop? Interestingly, Turing had very different ideas on these questions than the founders of cognitive science, like Noam Chomsky. And while the Chomskyan paradigm was dominant for most of the rest of the 20th century, in recent years, it has seemed more plausible that the Turing paradigm may be more relevant. Now, 2 years after this paper was published, there was a burglary at Alan Turing's house. And his boyfriend at the time happened to know the person who had done it. So Turing told the police about this. But under British law at the time, it was illegal to be gay. And so instead of prosecuting the burglar, the police prosecuted Turing. And under the advice of his family, he pled guilty and was able to avoid jail time by instead accepting mandatory hormone treatment with estrogen that was meant to feminize his body and suppress his sexuality. And this ended up being too much for him. And after a couple months of this treatment, he committed suicide by eating a cyanide-laced apple. It wasn't until many decades later, in 2009, that the British government finally apologized for its role in killing the person who had saved their country during the war and had originated the general idea of computation, which has been, as I said, incredibly important for the entire world. Okay, so let's begin this paper, Computing Machinery and Intelligence. Section 1, the imitation game. I propose to consider the question, can machines think? This should begin with definitions of the meaning of the terms machine and think. The definitions might be framed so as to reflect, so far as possible, the normal use of the words. But this attitude is dangerous. If the meaning of the words machine and think are to be found by examining how they are commonly used, it is difficult to escape the conclusion that the meaning and the answer to the question, can machines think, is to be sought in a statistical survey, such as a Gallup poll. But this is absurd. Interestingly, this very idea is one that many philosophers come back to 50 years later. They start getting interested in how do people actually use ordinary words, and do their ordinary uses of those words agree with the uses that philosophers want to make of them? Now, Turing is interested in the question, what should we be thinking about here, not what do ordinary people mean? And so he says, instead of attempting such a definition, I shall replace the question by another, which is closely related to it and is expressed in relatively unambiguous words. The new form of the problem can be described in terms of a game, which we call the imitation game. And so here he's going to give not the imitation game for identifying can a machine think, but a model of this game that we can then transfer to that one. So he says, this game is played with 3 people, a man A, a woman B, and an interrogator C, who may be of either sex. The interrogator stays in a room apart from the other 2. The object of the game for the interrogator is to determine which of the other 2 is the man and which is the woman. He knows them by labels X and Y, and at the end of the game, he says either X is A and Y is B, or X is B and Y is A. That is, the interrogator is trying to figure out which of them is the man and which of them is the woman. And the interrogator is allowed to put questions to A and B thus. So for instance, Will X please tell me the length of his or her hair? Now, suppose that X is actually A, the man. Then he must answer. It is his object in the game to try and cause C to make the wrong identification. His answer might therefore be, my hair is shingled and the longest strands are about 9 inches long. So he's saying the person's allowed to lie, or presumably tell the truth if that is actually what the man's hair is like. But he says, in order that tones of voice may not help the interrogator, the answers should be written, or better still, typewritten. Note, this is 1950 he's talking about. So no one who's reading this paper has an experience of text messages or internet chat. Alan Turing did, during the war, receive teletexted messages from the sites where they were actually recording the German messages and sending them to Bletchley Park. But this was not an experience that most people would have had. And so he says the ideal arrangement is to have a teleprinter communicating between the two rooms. Or alternatively, the question it answers could be repeated by an intermediary. The object of the game for the third player, B, the woman, is to help the interrogator. The best strategy for her is probably to give truthful answers. She can add such things as, I am the woman, don't listen to him, to her answers, but it will avail nothing as the man can make similar remarks. And so here he's describing this game where you've got a man and a woman, and the man is pretending to be a woman. And what he's going to suggest is a similar game where you have a computer and a human, and the computer is pretending to be a human. And the eventual idea he's going to suggest is, if the computer can convince the interrogator that they're a human throughout no matter how long the interaction goes, then we might as well just say that the computer is thinking. And now Turing doesn't say this about the man and the woman, but I think it's very natural to think about this. If a man can pass as a woman in as many interactions as you want, does it even make sense to say that he's not a woman? Turing doesn't address that question, but I think it's one that many people might pick up on from this initial discussion. So we now ask the question, what will happen when a machine takes the part of A in this game? Will the interrogator decide wrongly just as often when the game is played like this as he does when the game is played between a man and a woman? These questions replace our original, can machines think? That is, he's not interested in the question, what's going on inside the machine? He's just interested in the question, can we get everyone to agree that this machine is doing everything just the same way that a person is, so that we interact with it just as a person? Section 2, critique of the new problem. As well as asking, what is the answer to this new form of the question? One may ask, is this new question a worthy one to investigate? And so this latter question we investigate without further ado, thereby cutting short an infinite regress. That is, he's going to say, whether or not a machine can pass this test, it'll be an interesting question to figure out whether or not they can. So he's going to point out, this is an interesting question, whether or not you think it answers the question, can a machine think? He wants to claim this is a precise and answerable question that does all the work that matters of the original question, can a machine think? But whether or not you admit that, you should still admit this is an interesting question. Can a machine imitate a human to the extent that no one will ever know the difference? The new problem has the advantage of drawing a fairly sharp line between the physical and the intellectual capacities of a man. No engineer or chemist claims to be able to produce a material which is indistinguishable from human skin. It is possible that at some time this might be done, but even supposing this invention available, we should feel there was little point in trying to make a thinking machine more human by dressing it up in such artificial flesh. That's a really interesting point. The word robot was not in standard terminology at this time, but he's suggesting it's not about the body. What we care about when someone thinks is not what their skin is like. The form in which we have set this problem reflects this fact in the condition which prevents the interrogator from seeing or touching the other competitors or hearing their voices. Some other advantages of the proposed criterion may be shown up by specimen questions and answers. Thus, so here he's giving a little sample of what a dialogue might look like between a human and a computer or a human, where we don't know whether the answerer is a human or a computer. So the questioner asks, please write me a sonnet on the subject of the fourth bridge. And the answerer says, count me out on this one. I never could write poetry. I think he's imagining that answer because he's thinking, maybe it'll be hard for a computer to write poetry, but plenty of people think it's very hard to write poetry too. Of course, in the past year, ChatGPT has shown that actually computers can write poetry very quickly and easily, much more than most people. Next question. Add 34,957 to 70,764. And then the answerer pauses about 30 seconds, and then eventually gives the answer, 105,621. Now here, again, we can't tell. This sounds like a human because they took a long time to do the calculation, unlike a computer. Interestingly, they also got the calculation wrong. The correct answer is 105,721. But of course, a computer could be programmed to just delay the answer and give the wrong answer. Okay, do you play chess? Yes. Okay, I have my king at k1 and no other pieces. You have only your king at k6 and your rook at r1. It is your move. What do you play? So here he's describing a setup of the chessboard, which some of you may understand and some of you may not. After a pause of 15 seconds, r to r8, mate. And this is, I believe, a correct solution to the problem. Okay, so he says, the question and answer method seems to be suitable for introducing almost any one of the fields of human endeavor that we wish to include. We do not wish to penalize the machine for its inability to shine in beauty competitions, nor to penalize a man for losing in a race against an airplane. The conditions of our game make these disabilities irrelevant. The witnesses can brag if they consider it advisable as much as they please about their charms or strength or heroism, but the interrogator cannot demand practical demonstrations. And so here, note, he's saying, if we're interested in the question, can a machine think? We care, can it write poetry? Can it do math? Can it solve chess? These are the sorts of things that we think of as thinking. We don't think of how nice your skin looks or how fast you can run as an aspect of thinking or intelligence. And so he's saying this method of text, question, and answer is all you need to investigate the question of thinking. So now he says, the game may perhaps be criticized on the ground that the odds are weighted too heavily against the machine. If the man were to try and pretend to be the machine, he would clearly make a very poor showing. He would be given away at once by slowness and inaccuracy in arithmetic. Yeah, if you wanted a human to pretend to be a machine and you asked an arithmetic question that involved a 20-digit number, the machine could very instantly answer that question accurately, while the human could not. And so there's no way for the human to imitate a machine successfully in this game. And so he's suggesting, some people might think, well, if a human can't possibly imitate a machine, why would we ever think that a machine could imitate a human? And he says, may not machines carry out something which ought to be described as thinking, but which is very different from what a man does? He says, this objection is a very strong one, but at least we can say that if, nevertheless, a machine can be constructed to play the imitation game satisfactorily, we need not be troubled by this objection. So he's saying, this test may be stacked against the machine just the way that the parallel test would be stacked against the human. But if the machine could pass it, that's really impressive, regardless of whether or not the game is the correct one. It might be urged that when playing the imitation game, the best strategy for the machine may be something other than imitation of the behavior of a man. So this is an interesting point. Maybe you don't pretend to be like a normal human. Maybe you pretend to be like some caricature of a human, and that makes people think that you're a human. This may be, but I think that it is unlikely that there's any great effect of this kind. In any case, there is no intention to investigate here the theory of the game, that is the best strategy for playing this game. And it will be assumed that the best strategy is to try to provide answers that would naturally be given by a man. Section 3, the machines concerned in the game. The question which we put in Section 1 will not be quite definite until we have specified by what we mean by the word machine. So remember, this is 1950. His audience has not seen a computer. It is natural that we should wish to permit every kind of engineering technique to be used in our machines. They hadn't yet settled on what's the best way to build a computer. They didn't know. I mean, as I said, they hadn't invented the silicon transistor yet, let alone all the other things that we now think of as standard. We also wish to allow the possibility that an engineer or team of engineers may construct a machine which works, but whose manner of operation cannot be satisfactorily described by its constructors, because they have applied a method which is largely experimental. This turns out to be a lot of what's going on with modern neural networks. We understand many of the features of how those work, but not all of them. And he's already here noting that maybe we'll develop a computing machine that has that sort of feature. Finally, we wish to exclude from the machines men born in the usual manner. It is difficult to frame the definition so as to satisfy these three conditions. One might, for instance, insist that the team of engineers should all be of one sex, but this would not really be satisfactory, for it's probably possible to rear a complete individual from a single cell of the skin, say, of a man. To do so would be a feat of biological technique deserving of the very highest praise, but we would not be inclined to regard it as a case of constructing a thinking machine. That is, he's saying, if you were to give birth to a baby and raise it, and just call the baby the machine, of course it would pass. But that's not what we mean. And so this, he thinks, prompts us to abandon the requirement that every kind of technique should be permitted. The usual way of creating a baby is not a way of creating a thinking machine that is relevant to this question. We are more ready to do so in view of the fact that the present interest in thinking machines has been aroused by a particular kind of machine, usually called an electronic computer or a digital computer. Following this suggestion, we only permit digital computers to take part in our game. That's already an interesting limitation. If someone were to build a machine in some other way that somehow passes this test, that would also be impressive. But at this point, Turing is convinced that these digital computers are universal enough and can imitate anything that any computer could do, including the kinds of computers that humans are, he thinks, that he's confident that a digital computer would eventually be able to pass this. This restriction appears at first sight to be a very drastic one. I shall attempt to show that it is not so in reality. To do this necessitates a short account of the nature and properties of these computers. It may also be said that this identification of machines with digital computers, like our criterion for thinking, will only be unsatisfactory if, contrary to my belief, it turns out that digital computers are unable to give a good showing in the game. There are already a number of digital computers in working order, and it may be asked, why not try the experiment straight away? It would be easy to satisfy the conditions of the game. A number of interrogators could be used, and statistics compiled to show how often the right identification was given. The short answer is that we are not asking whether all digital computers would do well in the game, nor whether the computers at present available would do well, but whether there are imaginable computers which would do well. But this is only the short answer. We shall see this question in a different light later. Note, Turing is really thinking about his audience here. Most of these people have never interacted with a computer, and so they have no idea that the computers that they're working with at that time are doing complicated arithmetic and things like breaking codes, but aren't doing anything like having a conversation yet. To those of us in the present who are familiar with many different types of chatbots and many different types of phones and calculators and computers and stuff, it's not surprising that there are plenty of computers that can't pass the test, but maybe some that can. Whereas he's trying to help get his audience get the understanding that current computers are nowhere near this, and yet they seem to have the potential to do this. Okay, section 4, digital computers. And this is where he's going to give the outlines of a description of a Turing machine, but it's not in as much detail as his 1936 paper does. The idea behind digital computers may be explained by saying that these machines are intended to carry out any operations which could be done by a human computer. Note, when he says a human computer, computer was not the name of a machine in 1950. computer was the name of a job. There were people who worked for accounting companies, who worked for other kinds of companies, whose job was to just sit in a room and do computations all day for other people. And these computers played an important role in the war effort and in many different businesses at the time. And they would be familiar to his audience. And he's trying to say, a machine could do that. The human computer is supposed to be following fixed rules. He has no authority to deviate from them in any detail. That is, you give the computer some inputs and some rules, and you tell him, you apply these calculations, do this, and tell me what comes out at the end. We may suppose that these rules are supplied in a book, which is altered whenever he's put onto a new job. He also has an unlimited supply of paper on which he does his calculations. He may also do his multiplications and additions on a desk machine, but this is not important. A desk machine is one of the sort of mechanical adding and multiplying machines that many people would have been familiar with at this time. But human computers were still very important for doing all sorts of different complicated calculations, whether it's calculating rocket trajectories or making sales forecasts or whatever it is. If we use the above explanation as a definition, we shall be in danger of circularity of argument. We can avoid this by giving an outline of the means by which the desired effect is achieved. That is, it's not enough to just say, you give the person some rules and they follow them. You have to say what kinds of rules are the kinds of rules that they can do. Because otherwise, a rule that you give them is just solve the problem of world hunger. That's a task the computer could do, right? No? You want to give them instructions that they can follow where it says, apply this to that, do this, do that, and then we can interpret the result as doing something that we care about. So he says, a digital computer can usually be regarded as consisting of three parts. 1, store. 2, executive unit. 3, control. The store is a store of information, and it corresponds to the human computer's paper, whether this is the paper on which he does his calculations or that on which his book of rules is printed. Insofar as the human computer does calculations in his head, a part of the store will correspond to his memory. The executive unit is the part which carries out the various individual operations in the calculation. What these individual operations are will vary from machine to machine. Usually, fairly lengthy operations can be done, such as multiply 35406754445 by 707634567. But in some machines, only very simple ones, such as write down 0, are possible. And this is an interesting point. In the 1936 definition of a machine, the only instructions he allowed are move one step forward on the paper, move one step back on the paper, replace the symbol that you're looking at by one of the other symbols, and change which state of memory you're in. Those are the only instructions he allowed, and yet he proved a machine that knows how to do those instructions could be programmed to yield the result of any sort of calculation. By 1950, they already were building computers that could do more complicated instructions in a single step in order to simplify and shorten the calculations. But the important point is, it's only simple mechanical things that are allowable instructions. So he says, we have mentioned that the book of rules supplied to the computer is replaced in the machine by a part of the store. It is then called the table of instructions. It is the duty of the control to see that these instructions are obeyed correctly and in the right order. The control is so constructed that this necessarily happens. So this is a part of a computer that we don't often think about, but it's the processing unit that follows the instructions and ensures that whatever instructions are sent actually get carried out the way that they're described. The information in the store is usually broken up into packets of moderately small size. In one machine, for instance, a packet might consist of 10 decimal digits. Numbers are assigned to the parts of the store in which the various packets of information are stored in some systematic manner. A typical instruction might say, add the number stored in position 6809 to that in 4302, and put the result back into the latter storage position. Needless to say, it would not occur in the machine expressed in English. It would be more likely encoded in a form such as 6809430217, Here, the 6809 tells you the first location, 4302 tells you the second location, and 17 tells you which operation to do on the two numbers. In this case, the operation 17 is add the number and put it into the second place. It will be noted that the instruction takes up 10 digits and so forms one packet of information very conveniently. That is, he has 4-digit locations of memory stores and 2-digit instructions so that a single instruction takes 10 digits, and that corresponds to the packet of the information in a computer. This is a thing that we might have heard about in later decades when people talk about 8-bit machines or 16-bit machines or 64-bit machines. These correspond to how big are these instructions that the machine can do. The control will normally take the instructions to be obeyed in the order of the positions in which they're stored, but occasionally an instruction such as, now obey the instruction stored in position 5606 and continue from there, may be encountered. Or again, if position 4505 contains 0, obey next the instruction stored in 6707, otherwise continue straight on. So these are important tools in computer programming, these if statements and these go-to statements. Instructions of these latter types are important because they make it possible for a sequence of operations to be repeated over and over again until some condition is fulfilled. But in doing so, they obey not fresh instructions on each repetition, but the same ones over and over again. To take a domestic analogy, suppose mother wants Tommy to call at the cobbler's every morning on his way to school to see if her shoes are done. She can ask him afresh every morning. Alternatively, she can stick up a notice once and for all in the hall, which he will see when he leaves for school, and which tells him to call for the shoes, and also to destroy the notice when he comes back if he has the shoes with him. So that is, every morning mom could tell you, go check by the shoe store, see if my shoes are ready. Or she could put up a note that says, as long as this note is up, check the shoe store every morning. If the shoes are ready, take down this note. And that's the sort of thing a computer can do. The reader must accept it as a fact that digital computers can be constructed and indeed have been constructed according to the principles we've described, and that they can in fact mimic the actions of a human computer very closely. The book of rules which we have described our human computer as using is, of course, a convenient fiction. Actual human computers really remember what they have got to do. If one wants to make a machine mimic the behavior of the human computer in some complex operation, one has to ask him how it is done and then translate the answer into the form of an instruction table. Constructing instruction tables is usually described as programming. To program a machine to carry out the operation A means to put the appropriate instruction table into the machine so that it will do A. An interesting variant on the idea of a digital computer is a digital computer with a random element. These have instructions involving the throwing of a die or some equivalent electronic process. One such instruction might be, for instance, throw the die and put the resulting number into store 1000. Sometimes such a machine is described as having free will, though I would not use this phrase myself. Yeah, and this is an interesting point. Most computer scientists these days would not at all describe randomness as free will. But I think in the late 1940s, a few computer scientists who, of course, didn't even yet have the word computer science might have thought, well, all our machines so far only always follow the instruction the same way every time. We allow some randomness here. This is like free will, but it's really not. Now he says, it is not normally possible to determine from observing a machine whether it has a random element, for a similar effect can be produced by such devices as making the choices depend on the digits of the decimal for pi. And as a matter of fact, most modern computers don't have anything that claims to be really random. What they usually do is they just look at the system clock and see how many milliseconds it's been since something, and they use that number as their random number. And that's good enough for any purpose. And there's an interesting and important philosophical question about whether any more real form of randomness is even possible. Most actual digital computers have only a finite store. There is no theoretical difficulty in the idea of a computer with an unlimited store. Of course, only a finite part can have been used at any one time. So that is, imagine a person who has an infinite stack of paper that they're allowed to use for doing their calculations so that they never run out. At any point, they'll only have ever used finitely much of it. But it is important to assume that they always have more paper available if necessary. And similarly, he's saying, theoretically, it's useful to assume that a computer always has more digital storage available if necessary. Likewise, only a finite amount can have been constructed, but we can imagine more and more being added as required. Such computers have special theoretical interest and will be called infinitive capacity computers. The idea of a digital computer is an old one. Charles Babbage, Lucasian professor of mathematics at Cambridge from 1828 to 1839, planned such a machine called the analytical engine, but it was never completed. Although Babbage had all the essential ideas, his machine was not at that time such a very attractive prospect. The speed which would have been available would be definitely faster than a human computer, but something like 100 times slower than the Manchester machine, itself one of the slower of the modern machines. The storage was to be purely mechanical, using wheels and cards. The fact that Babbage's analytical engine was to be entirely mechanical will help us to rid ourselves of a superstition. Importance is often attached to the fact that modern digital computers are electrical and that the nervous system is also electrical. But since Babbage's machine was not electrical, and since all digital computers are in a sense equivalent, we see that this use of electricity cannot be of theoretical importance. Of course, electricity usually comes in where fast signaling is concerned, so that it is not surprising that we find it in both of these connections. In the nervous system, however, chemical phenomena are at least as important as electrical. And in certain computers, the storage system is mainly acoustic. This is interesting. In the computers that they built in the 1940s, often they didn't have yet modern magnetic memory for computers. The way they worked was they had a tube of mercury and they would just code a vibration in that tube that bounced back and forth, and they would listen to that vibration whenever they needed to get the store. And it's surprising, but that actually worked. The feature of using electricity is thus seen to be only a very superficial similarity. If we wish to find such similarities, we should look rather for mathematical analogies of function. This is an important point that many philosophers of mind have picked up later, that what matters is the structure of the relationships of the things that are going on, not the actual physical means by which it happens. Section 5, Universality of Digital Computers. The digital computers considered in the last section may be classified amongst the discrete state machines. These are the machines which move by sudden jumps or clicks from one quite definite state to another. You can imagine a clock where the second hand ticks every second. And a clock is obviously a very simple discrete state machine. It only does one very simple type of computation, and it can't be programmed to do many others. The interesting thing Turing is going to show here is that these digital computers can do anything that any other discrete state machine can do. These states, the important point about them being discrete states where there's a sudden jump from one to the next, is that they are sufficiently different for the possibility of confusion between them to be ignored. Strictly speaking, there are no such machines. Everything really moves continuously. But there are many kinds of machine which can profitably be thought of as being discrete state machines. For instance, in considering the switches for a lighting system, it is a convenient fiction that each switch must be definitely on or definitely off. Think about that. If you go to the wall and try to hit the light switch, you can move it continuously from off to on. And it's just that it's designed in a way that if it's at all close to on, it'll click into the on position. And if it's at all close to off, it'll click into the off position. And then there's a connection in the wires there. If you were really careful, you could probably get the connection to be very close and get electricity to flow just a little bit across there so that the light partly turns on. But because of how the system is set up, most of the time, 99.99999% of the time, it's just flowing or not flowing. And so we can pretend that there's no other way for the light to be other than on or off. There must be intermediate positions, but for most purposes, we can forget about them. As an example of a discrete state machine, we might consider a wheel which clicks around through 120 degrees once a second. That is, it's a third of the way around, and then a third of the way around, and then back to the original position. but it may be stopped by a lever which can be operated from outside. In addition, a lamp is to light in one of the positions of the wheel. This machine could be described abstractly as follows. The internal state of the machine, which is described by the position of the wheel, may be Q1 or Q2 or Q3. There is an input signal, I0 or I1, which is the position of the lever. The internal state at any moment is determined by the last state and the input signal according to the table. And if we look here, when the switch is in I0, then at each point, Q1 moves to Q2, Q2 moves to Q3, Q3 moves to Q1. But in state I1, Q1 stays in I1, Q2 stays in I2, and Q3 stays in I3. The output signals, the only externally visible indication of the internal state, the light, are described by the table state in Q1, Q2, and Q3. In Q1 and Q2, the light is off, output 0, and in Q3, the light is on. This example is typical of discrete state machines. They can be described by such tables provided they have only a finite number of possible states. And interestingly, one thing here is you can't tell from the outside whether the machine is in state Q1 or in state Q2. All you can tell is whether it's in Q3 or not, and maybe by playing around with the switch, you could eventually figure out what's going on. And Turing's idea is that this is the same thing as what's going on in the human mind. There's something going on inside, but all you ever get to see is the text that comes in and out. And maybe that text is enough to figure out everything important about what's going on inside. And that is the central question of intelligence or cognitive science. It will seem that given the initial state of the machine and the input signals, it is always possible to predict all future states. This is reminiscent of Laplace's view that from the complete state of the universe at one moment of time, as described by the positions and velocities of all particles, it should be possible to predict all future states. The prediction which we are considering is, however, rather nearer to practicability than that considered by Laplace. The system of the universe as a whole is such that quite small errors in the initial conditions can have an overwhelming effect at a later time. So this is an important point. Laplace was an important mathematician and physicist of the late 18th century who, after having understood Newton's system and the other kinds of systems of physics that were going on, he realized we can calculate how everything will behave if we just know where everything is right now. And maybe this is how God works, is his thought. That God set up the initial conditions of the universe and set up the laws and therefore knows everything about how the universe will be at every state. But what many people observed later on is that even just a tiny error, the displacement of a single electron by a billionth of a centimeter at one moment, might make the difference between a man being killed by an avalanche a year later or escaping. These days, this is often called the butterfly effect, that the flapping of the wings of a butterfly make a slight difference to the gusts of wind in the area, and maybe that makes a slight difference as to whether the rain starts falling here 1 second earlier or later, which then makes a difference to whether the river has enough flow to do whatever later, which then eventually causes some hurricane or prevents a hurricane. Now, interestingly, it is an essential property of the mechanical systems which we have called discrete state machines that this phenomenon does not occur. That is, any slight error in the initial state ends up being treated as though it's the same state. If the clock is not pointing precisely at the second but is slightly off, if it's still ticking 1 second per second, then you can predict what it's going to do, even though you don't know precisely to the margin of a hair where it's going to be pointing. And similarly, if your computer is calculating by a digital device like this, it doesn't matter if it's slightly warmer or slightly cooler, or if an electron fires slightly differently. The device is built in such a way that it's robust against tiny errors, and it's just the computation that matters. Even when we consider the actual physical machines instead of the idealized machines, reasonably accurate knowledge of the state at one moment yields reasonably accurate knowledge any number of steps later. If you know the instructions, you can compute exactly what it's going to do. As we've mentioned, digital computers fall within the class of discrete state machines. But the number of states of which such a machine is capable is usually enormously large. So that is, he was initially discussing a machine with 3 states. A clock might be a machine with 60 states or 525,600 states or whatever. But he says the number for the machine now working at Manchester is about 2 raised to the power of 165,000, i.e. about 10 raised to the power of 50,000. That is, this is a 50,000 digit number that describes how many states there are. And the reason is basically because the Manchester machine had something like 165,000 initial switches that could all be on or off. Compare this with our example of the clicking wheel described above, which had 3 states. It is not difficult to see why the number of states should be so immense. The computer includes a store corresponding to the paper used by a human computer. It must be possible to write into the store any one of the combinations of symbols which might have been written on the paper. For simplicity, suppose that only digits from 0 to 9 are used as symbols, and variations in handwriting are ignored. Suppose the computer is allowed 100 sheets of paper, each containing 50 lines with room for 30 digits. Then the number of states is 10 raised 10 for each digit, raised to the power 100 times 50 times 30. There's 100 pages of 50 lines of 30 symbols. So there's 10 to the 150,000 possible sets of things that could be written down on the sheets. This is about the number of states of 3 of the Manchester machines put together. That's just 100 pages of text. The logarithm to the base 2 of the number of states is usually called the storage capacity of the machine. In modern terminology, we call this bits, but Turing doesn't have that word yet. Thus, the Manchester machine has a storage capacity of about 165,000, and the wheel machine of our example about 1.6. If 2 machines are put together, their capacity is added to obtain the capacity of the resulting machine. This leads to the possibility of statements such as, the Manchester machine contains 64 magnetic tracks, each with a capacity of 2,560 bits, 8 electronic tubes with a capacity of 1,280 bits. Miscellaneous storage amounts to about 300 bits, making a total of 174,380 bits. Given the table corresponding to a discrete state machine, it is possible to predict what it will do. There is no reason why this calculation should not be carried out by means of a digital computer. This is the basic idea. If you have any finite state machine, a digital computer can compute what that machine will do. And that is why digital computers are universal. They can understand what any other machine can do. Provided it could be carried out sufficiently quickly, the digital computer could mimic the behavior of any discrete state machine. The imitation game could then be played with the machine in question as B, and the mimicking digital computer as A, and the interrogator would be unable to distinguish them. So this is the important point. Even though the machines are internally different, the one machine is able to perfectly imitate the other so that there's no way to distinguish them. And he thinks if that's going on, then we don't care about the difference between those machines. And this is what motivates him in proposing the Turing test for distinguishing the intelligence of a computer from the intelligence of a human. If it can perfectly mimic a human, then it doesn't really matter what's going on inside, whether it's the same or something that is functionally equivalent. Of course, the digital computer must have an adequate storage capacity as well as working sufficiently fast. Moreover, it must be programmed afresh for each new machine which it is desired to mimic. This special property of digital computers, that they can mimic any discrete state machine, is described by saying that they are universal machines. The existence of machines with this property has the important consequence that, considerations of speed apart, it is unnecessary to design various new machines to do various computing processes. They can all be done with one digital computer suitably programmed for each case. It will be seen that as a consequence of this, all digital computers are in a sense equivalent. And this is really important. We are now familiar with the idea that you can just download a new program and install it on your computer, and your computer can now do a thing that it couldn't do before. But in the mid-20th century, people were familiar with the idea that if you build a machine, it does one thing. And if you want a machine to do something else, you need to build a new machine. But the digital computer changed all that. You can just download a program and it can now do something that it couldn't do before. and it can do anything that any other finite state machine can do. We may now consider again the point raised at the end of section 3. It was suggested tentatively that the question, can machines think, should be replaced by, are there imaginable digital computers which would do well in the imitation game? If we wish, we can make this superficially more general and ask, are there discrete state machines which would do well? But in view of the universality property, we see that either of these questions is equivalent to this. Let us fix our attention on one particular digital computer C. Is it true that by modifying this computer to have an adequate storage, suitably increasing its speed of action, and providing it with an appropriate program, C can be made to play satisfactorily the part of A in the imitation game, the part of B being taken by a man? Note, he's already identified all you need is more memory, a faster computer, and maybe the right program. Section 6, contrary views on the main question. So this, I think, is one of the most important sections where he's seeing what are the challenges to the claim that a computer could pass the Turing test. We may now consider the ground to have been cleared, and we are ready to proceed to the debate on our question, can machines think? And the variant of it quoted at the end of the last section. That is, could a machine work in the imitation game to such a level that no one would ever know the difference? We cannot altogether abandon the original form of the problem, for opinions will differ as to the appropriateness of the substitution, and we must at least listen to what has to be said in this connection. It will simplify matters for the reader if I explain first my own beliefs in the matter. Consider first the more accurate form of the question. I believe that in about 50 years' time, it will be possible to program computers with a storage capacity of about 10 to the 9th to make them play the imitation game so well that an average interrogator will not have more than 70% chance of making the right identification after 5 minutes of questioning. Let me just say, what does he say there? So he, in 1950, predicted that by the year 2000, there would be computers that have a gigabyte of storage and that would be able to play the imitation game, at least to the point of fooling people for 5 minutes into thinking that they're human. Turns out that's almost right. I believe a gigabyte of storage probably came right around the year 2000, just as he predicted. I don't think there were any computers that fooled expert interrogators for 5 minutes at 2000, but there have been since. And in fact, if any of you have ever interacted on Twitter or on phone chat helpline with certain bots, you may have been fooled for 5 minutes. But I think even in the 1960s, there were already some computers that were fooling some people without doing anything significant at all. So he says, so his prediction was pretty close to spot on, especially given that he was forecasting 50 years of the development of computing technology. The original question, can machines think, I believe to be too meaningless to deserve discussion. Nevertheless, I believe that at the end of the century, the use of words and general educated opinion will have altered so much that one will be able to speak of machines thinking without expecting to be contradicted. I'm not sure if that's exactly right. I don't think in the year 2000 people were seriously saying things about their computer thinking. But I think it was very common in the year 2000 for people who were doing some long, complicated process on the computer to say, oh, my computer's still thinking, it's still calculating, it's still working on that. Or look at that, my computer thinks that it's 1950 again because it failed the Y2K problem. We talked as though computers think, even though we didn't really think that they think. Now, nowadays, I think we're getting much closer. And then he says, I believe further that no useful purpose is served by concealing these beliefs. The popular view that scientists proceed inexorably from well-established fact to well-established fact, never being influenced by any unproved conjecture, is quite mistaken. Provided it is made clear which are proved facts and which are conjectures, no harm can result. Conjectures are of great importance since they suggest useful lines of research. So here he's saying he's not going to pretend that he doesn't know the answer to this question. He thinks that computers will be able to think in every sense that really matters, a little bit by the end of the 20th century and more soon after. But he hasn't proven that. All he has proven is that digital computers can be universal, and then he conjectures that the human mind is one of the things that they can imitate. I now proceed to consider opinions opposed to my own. Objection 1, the theological objection. Thinking is a function of man's immortal soul. God has given an immortal soul to every man and woman, but not to any other animal or to machines. Hence, no animal or machine can think. That's an objection. He says, I am unable to accept any part of this, but will attempt to reply in theological terms. And he says, I should find the argument more convincing if animals were classed with men, for there's greater difference to my mind between the typical animate and the inanimate than there is between man and the other animals. And this is an interesting point. Can animals think? The arbitrary character of the orthodox view becomes clearer if we consider how it might appear to a member of some other religious community. How do Christians regard the Muslim view that women have no souls? I don't believe that's an accurate view of Islam, but it may be that there are branches of Islam that make that claim. And I think that raises the interesting question. If you think that men and women have souls, how do you object to the people who claim that only men do and women don't? Or if you think that people of all races have souls, how do you object to the people who claim that white people do and black people don't? If you claim that all animals have souls, how do you object to the people that claim that only humans have souls? But let us leave this point aside and return to the main argument. It appears to me that the argument quoted above implies a serious restriction of the omnipotence of the Almighty. It is admitted that there are certain things that he cannot do, such as making 1 equal to 2, but should we not believe that he has freedom to confer a soul on an elephant if he sees fit? We might expect that he would only exercise this power in conjunction with a mutation which provided the elephant with an appropriately improved brain to minister to the needs of this soul. But now an argument of exactly similar form may be made for the case of machines. It may seem different because it's more difficult to swallow, but this really only means that we think it would be less likely that he would consider the circumstances suitable for conferring a soul. The circumstances in question are discussed in the rest of this paper. In attempting to construct such machines, we should not be irreverently usurping his power of creating souls, any more than we are in the procreation of children. Rather, we are, in either case, instruments of his will, providing mansions for the souls that he creates. So that is the idea, he thinks. If you really claim that animals don't have souls, the best reason for that is presumably thinking that animals don't do all the complicated cognitive things that souls are needed for. And if some animal were by chance to do that, then maybe God would give that animal a soul. And he says, if you thought that, then why not think the same thing about machines? However, this is mere speculation. I'm not very impressed with theological arguments, whatever they may be used to support. Such arguments have often been found unsatisfactory in the past. In the time of Galileo, it was argued that the texts, and the sun stood still and hasted not to go down about a whole day, and he laid the foundations of the earth that it should not move at any time, were an adequate refutation of the Copernican theory. With our present knowledge, such an argument appears futile. When that knowledge was not available, it made a quite different impression. Objection 2, the head in the sand objection. The consequences of machines thinking would be too dreadful. Let us hope and believe they cannot do so. I think this one you may hear more explicitly more often these days than you used to. He says this argument is seldom expressed quite so openly as in the form above, but it affects most of us who think about it at all. We like to believe that man is in some subtle way superior to the rest of creation. It is best if we can be shown to be necessarily superior, for then there is no danger of us losing our commanding position. The popularity of the theological argument is clearly connected with this feeling. It is likely to be quite strong in intellectual people, since they value the power of thinking more highly than others, and are more inclined to base their belief in the superiority of man on this power. I do not think that this argument is sufficiently substantial to require refutation. Consolation would be more appropriate. Perhaps this should be sought in the transmigration of souls. So he's just saying, think about how awful it would be if humans were not the only beings that thought. And if we can think that is so awful, then let's just not even consider the question. And he thinks that's not an objection. Objection 3, the mathematical objection. There are a number of results of mathematical logic which can be used to show that there are limitations to the powers of discrete state machines. The best known of these results is known as Gödel's theorem, and shows that in any sufficiently powerful logical system, statements can be formulated which can neither be proved nor disproved within the system, unless possibly the system itself is inconsistent. There are other, in some respects, similar results due to Church, Kleene, Rosser, and Turing. The latter result, which is his own, of course, is the most convenient to consider since it refers directly to machines, whereas the others can only be used in a comparatively indirect argument. For instance, if Gödel's theorem is to be used, we need in addition to have some means of describing logical systems in terms of machines and machines in terms of logical systems. This is all stuff that Turing did in earlier work. The result in question refers to a type of machine which is essentially a digital computer with an infinite capacity. So this is Turing describing the result on Turing machines that shows they cannot determine whether or not an arbitrary Turing machine is going to crash. It states that there are certain things that such a machine cannot do. If it is rigged up to give answers to questions, as in the imitation game, there will be some questions to which it will either give a wrong answer or fail to give an answer at all, however much time is allowed for a reply. There may, of course, be many such questions, and questions which cannot be answered by one machine may be satisfactorily answered by another. We, of course, are supposing for the present that the questions are of the kind to which the answer yes or no is appropriate, rather than questions such as, what do you think of Picasso? The questions that we know the machine must fail on are of this type. Consider the machine specified as follows. Will this machine ever answer yes to any question? That is, if Apple is trying to decide, how can we prevent our phone from ever crashing? They might be confronted with the question, the user's trying to download a program. Is this a program which is ever going to crash? And what Turing showed is there is no computer program that can answer the question in general, which programs will crash and which programs won't. And that's why even Apple can't prevent the devices from ever crashing. So he says the dots are to be replaced by a description of some machine in a standard form, which could be something like that used in section 5. When the machine described bears a certain comparatively simple relation to the machine which is under interrogation, it can be shown that the answer is either wrong or not forthcoming. Basically, you ask the computer, here's a program for checking whether programs will crash. Let's run this program on itself and see if it will ever crash. And you set it up in such a way that it creates a paradox either way. This is the mathematical result. But it is argued it proves a disability of machines to which the human intellect is not subject. The short answer to this argument is that although it is established that there are limitations to the powers of any particular machine, it has only been stated without any sort of proof that no such limitations apply to the human intellect. This is a point that many people go on to try to argue in later decades. And in particular, the physicist Roger Penrose is one who has made this argument very strongly. He's trying to say there are certain things that the human intellect can do, that the machines can't, including solving certain halting problems. And he says, I do not think this view can be dismissed quite so lightly. Whenever one of these machines is asked the appropriate critical question, it gives a definite answer. We know that this answer must be wrong, and this gives us a certain feeling of superiority. Is this feeling illusory? It is no doubt quite genuine. It is a feeling, but I do not think too much importance should be attached to it. We, too, often give wrong answers to questions, and we do it too often to be justified in being very pleased at such evidence of fallibility on the part of the machines. Further, our superiority can only be felt on such an occasion in relation to the one machine over which we have scored our petty triumph. There'd be no question of triumphing simultaneously over all machines. the interesting thing that Turing shows, in addition to showing that no computer can answer the general question, which computer programs will crash, you can show that for any computer program that answers this question partially, there's another computer program that answers it better, and no program is better than all of the others. So he says, there would be no question of triumphing simultaneously over all machines. In short, then, there might be men cleverer than any given machine, but then again, there might be other machines that are cleverer again, and so on. Those who hold to the mathematical argument would, I think, mostly be willing to accept the imitation game as a basis for discussion, whereas those who believe in the two previous objections would probably not be interested in any criterion. Objection 4, the argument from consciousness. This argument is very well expressed in Professor Jefferson's Lister oration for 1949, from which I quote, "Not until a machine can write a sonnet or compose a concerto because of thoughts and emotions felt, and not by the chance fall of symbols, could we agree that machine equals brain. That is, not only write it, but know that it had written it. No mechanism could feel, and not merely artificially signal an easy contrivance, could feel pleasure at its successes, grief when its valve skews, or be warmed by flattery, or be made miserable by its mistakes, or be charmed by sex, or be angry or depressed when it cannot get what it wants." This argument appears to be a denial of the validity of our test. And that is, he's saying, he seems to be denying that even if the machine imitated all these emotions, that it would actually be feeling them. And so according to the most extreme form of this view, the only way by which one could be sure that a machine thinks is to actually be the machine and to feel oneself thinking. One could then describe these feelings to the world, but of course no one would be justified in taking any notice. But as Turing goes on to object, likewise, according to this view, the only way to know that a man thinks is to be that particular man. It is in fact the solipsist point of view. That is, he's saying, if all you're saying is that the imitation of emotion doesn't give us any reason to believe that there is real emotion there, then why should we think that anyone else other than ourselves has emotions? It may be the most logical view to hold, but it makes communication of ideas difficult. A is liable to believe A thinks, but B doesn't, while B believes B thinks, but A doesn't. Instead of arguing continually over this point, it's usual to have the polite convention that everyone thinks. We can never prove that the other people around us have minds, and it's easier, we all get along better if we just agree that we do, because everyone's talking as though they do. And I think Turing's idea is, if machines are able to participate in that conversation just as well, then we'll eventually come around to including them in this fiction. Or reality, whatever it is. Is there a real difference? That's the question that he's suggesting may not have a meaningful answer. I'm sure that Professor Jefferson does not wish to adopt the extreme and solipsist point of view. Probably he would be willing to accept the imitation game as a text. The game, with the player B omitted, is frequently used in practice under the name of viva voce to discover whether someone really understands something or has learnt it in parrot fashion. Let us listen in to a part of such a viva voce. So this is the idea of an oral exam, and this would be very common in Oxford and Cambridge, and it occasionally happens in many other contexts, where instead of asking the student to write out the answers to a test, you quiz the student, ask them, and don't just let them give the right answer. Ask them why that's the right answer. What thoughts led you to that? And then you can convince yourself that the student is really thinking, as opposed to just having memorized the answers as a parrot. So he says, interrogator, in the first line of your sonnet, which reads, "Shall I compare thee to a summer's day? Would not a spring day do as well or better?" Witness, it wouldn't scan. All right, so he's explained. Why is he saying summer's day rather than spring day? Interrogator, how about a winter's day? That would scan all right. Witness, yes, but nobody wants to be compared to a winter's day. That seems right. He's understanding some of the important difference between summer and winter. People like summer, people don't like winter. Interrogator, would you say Mr. Pickwick reminded you of Christmas? Witness, in a way. Yet Christmas is a winter's day, and I do not think Mr. Pickwick would mind the comparison. I don't think you're serious. By winter's day, one means a typical winter's day rather than a special one like Christmas. That all seems correct. This is all showing that the person is understanding what they're doing when they're writing the poem. It might be an interesting exercise to ask ChatGPT to write a poem and do this same sort of questioning. Why did it choose these words? Is it able to give answers that are as convincing as this? I haven't tried this. And so on. What would Professor Jefferson say if the sonnet writing machine was able to answer like this in the viva voce? I do not know whether he would regard the machine as merely artificially signaling these answers, but if the answers were as satisfactory and sustained as in the above passage, I do not think he would describe it as an easy contrivance. Because note, in order to give those answers, you had to have an understanding of meter and poetry and also emotional symbolism. And also, what do people feel about the seasons? And also, understanding the difference between typicality and individuality. Why is Christmas a nice thing to be compared to, but a winter's day not a nice thing to be compared to? Or what context might it be nice to compare someone to a winter's day? So he says, this phrase is, I think, intended to cover such devices as the inclusion in the machine of a record of someone reading a sonnet, with appropriate switching to turn it on from time to time. That is, if all that's happening is that we have a tape recording of the sonnet, that's not real emotion. But if the person is able to explain why every single word is chosen as it does and what emotions are being triggered by it, do we really want to deny that that person understands the emotions? In short, then, I think that most of those who support the argument from consciousness could be persuaded to abandon it rather than be forced into the solipsist position. They will then be probably willing to accept our test. Though notice, it's a test that's going to involve a lot of repeated interactions, not just a single 5-minute interaction. I do not wish to give the impression that I think there is no mystery about consciousness. There is, for instance, something of a paradox connected with any attempt to localize it. But I do not think that these mysteries necessarily need to be solved before we can answer the question with which we are concerned in this paper. That is, we don't need to say, are machines conscious, to answer, can machines think, or can machines be intelligent? Whatever the mysteries of consciousness are, they are separate from the mysteries of intelligence and thinking. Objection 5, arguments from various disabilities. These arguments take the form, I grant you that you can make machines do all the things you've mentioned, but you'll never be able to make one to do X. Numerous features X are suggested in this connection. I offer a selection. Being kind, resourceful, beautiful, friendly, having initiative, have a sense of humor, tell right from wrong, make mistakes, fall in love, enjoy strawberries and cream, make someone fall in love with it, learn from experience, use words properly, be the subject of its own thought, have as much diversity of behavior as a man, do something really new. Some of these disabilities are given special consideration as indicated by the page numbers. That is, each of these is going to be discussed on those pages of this paper. No support is usually offered for these statements. I believe they are mostly founded on the principle of scientific induction. That is the idea that you observe something a bunch of times and it's always a certain way, so you predict it'll always be that way. This is how we predict that the sun will rise, that gravity will continue to work, and so on. And so he says, a man has seen thousands of machines in his lifetime. From what he sees of them, he draws a number of general conclusions. They're ugly, each is designed for a very limited purpose. When required for a minutely different purpose, they are useless. The variety of behavior of any one of them is very small, etc., etc. Naturally, he concludes that these are necessary properties of the machines in general. Many of these limitations are associated with the very small storage capacity of most machines. This is an important point that he's already observing in 1950. The large amount of data and memory turns out to be really important. I'm assuming that the idea of storage capacity is extended in some way to cover machines other than discrete state machines. The exact definition doesn't matter, as no mathematical accuracy is claimed in this present discussion. A few years ago, when very little had been heard of digital computers, it was possible to elicit much incredulity concerning them if one mentioned their properties without describing their construction. Yeah, imagine thinking in 1945 Someone's built a machine that can crack German codes. At that point, the only machines people would be familiar with are things like weaving machines or stamping machines or plowing machines. How can a machine like that do something so intelligent as breaking a code? And so that was presumably due to a similar application of the principle of scientific induction. These applications of the principle are, of course, largely unconscious. When a burnt child fears the fire and shows that he fears it by avoiding it, I should say he was applying scientific induction, even though the child doesn't know that term and can't even necessarily explain why they're staying away from the fire. They just are. I could, of course, also describe the child's behavior in many other ways. The works and customs of mankind, however, do not seem to be very suitable material to which to apply scientific induction. A very large part of space-time must be investigated if reliable results are to be obtained. Otherwise, we may, as most English children do, decide that everybody speaks English and that it's silly to learn French. This is his point. Maybe it's reasonable to assume all birds behave the same because you've seen a bunch of birds. But once you've seen humans or machines, assuming that all humans work the same way because you've seen a bunch of humans, obviously silly, because then you'd think everyone speaks English. But of course, if you actually go around the world, you'll discover there's all sorts of different things people do. You might also think, no one's ever done such and such, so therefore no one will ever do that. But of course, people are breaking records and setting firsts all the time. And his point is the same is true with machinery. Just because no machine so far has done something doesn't mean no one will be able to come up with a machine that can. Now he says, there are, however, special remarks to be made about many of the disabilities that have been mentioned. The inability to enjoy strawberries and cream may have struck the reader as frivolous. Possibly a machine might be made to enjoy this delicious dish, but any attempt to make one do so would be idiotic. But what is important about this disability, however, he says, and I think he does think it is important, is that it contributes to some of the other disabilities, e.g. to the difficulty of the same kind of friendliness occurring between man and machine, as between white man and white man, or between black man and black man. Notice here, this comparison that he's drawing, I think, is very intentional. He's noting that one of the objections people have is that no machine could ever be friends with a human. But he's pointing out maybe the reason no machine could ever be friends with a human is because part of our friendship comes from enjoying some of the same foods, enjoying some of the same music. But that sort of friendship is not universal among humans. I'm not sure that his discussion of it is exactly right, but it's true that it's much more difficult to be close and friendly with someone who's lived in an entirely different culture their entire life than you do. You don't have a language in common, you don't enjoy the same foods, you don't enjoy the same music. Now, maybe they could learn to enjoy the same foods and could learn to enjoy the same music. But is that really what's important to them being intelligent? Could you grow to respect them even if they never enjoyed any of those things? And I think his thought is, we should think the same about machines. Maybe they will never have the same sort of physical pleasure and enjoyment that we do in certain physical activities. But maybe there are other things that they'll do that we never understand. But if we're still able to interact rationally through text, maybe that's enough to have friendship. So he says, the claim that machines cannot make mistakes seems a curious one. One is tempted to retort, are they any the worse for that? But let us adopt a more sympathetic attitude and try to see what is really meant. I think this criticism can be explained in terms of the imitation game. It is claimed that the interrogator could distinguish the machine from the man simply by setting them a number of problems in arithmetic. The machine would be unmasked because of its deadly accuracy. But the reply to this is simple. The machine, programmed for playing the game, would not attempt to give the right answers to the arithmetic problems. Remember his example earlier where the machine forgot to carry the one, or forgot to carry the one. It would deliberately introduce mistakes in a manner calculated to confuse the interrogator. A mechanical fault would probably show itself through as an unsuitable decision as to what sort of a mistake to make in the arithmetic. That is, if there was a literal bug in the machine, the word bug comes from actual bugs that got in the vacuum tubes early on, then it would probably just do something crazy instead of adding the numbers. But if it was programmed well, it could make realistic mistakes. But even this interpretation of the criticism is not sufficiently sympathetic. But we cannot afford the space to go into it much further. It seems to me that this criticism depends on a confusion between two kinds of mistake. We may call them errors of functioning and errors of conclusion. Errors of functioning are due to some mechanical or electrical fault which causes the machine to behave otherwise than it was designed to do. In philosophical discussions, one likes to ignore the possibility of such errors. One is therefore discussing abstract machines. These abstract machines are mathematical fictions rather than physical objects. By definition, they're incapable of errors of functioning. In this sense, we can truly say that machines can never make mistakes. Errors of conclusion can only arise when some meaning is attached to the output signals from the machine. The machine might, for instance, type out mathematical equations or sentences in English. When a false proposition is typed, we say that the machine has committed an error of conclusion. But there's clearly no reason at all for saying that a machine cannot make this kind of mistake. It could do nothing but type out repeatedly 0 equals 1, 0 equals 1. To take a less perverse example, it might have some method for drawing conclusions by scientific induction. That is, observe a bunch of fires, discover they're hot, and say, fire is always hot. Observe a bunch of ravens, see they're all black. Write down the sentence, ravens are black. Observe a bunch of swans, see that they're all white. Write down the sentence, all swans are white. But we must expect such a method to lead occasionally to erroneous results, because as we now know, not all swans are white. There are black swans in Australia. And so if the machine is programmed well, in this case, it will mostly make true statements, but sometimes come up with false ones. The claim that a machine cannot be the subject of its own thought can, of course, only be answered if it can be shown that the machine has some thought with some subject matter. Nevertheless, the subject matter of machines' operations does seem to mean something, at least to the people who deal with it. This is actually a question that's really important in philosophy of mind called the problem of intentionality. What is it for something to be, some thought to be about something? If, for instance, the machine was trying to find a solution of the equation x squared minus 40x minus 11 equals 0, one would be tempted to describe this equation as part of the machine's subject matter at that moment. But in this sort of sense, a machine undoubtedly can be its own subject matter. It may be used to help in making up its own programs, or to predict the effect of alterations in its own structure. By observing the results of its own behavior, it could modify its own programs so as to achieve some purpose more effectively. These are possibilities of the near future rather than utopian dreams. This is a really important point that many people have observed. If computers can be used to reason about computers. In fact, all modern computers are designed on computers. And in fact, computers can be used to design their own improvements. And some people are worried if an artificial intelligence is able to design its own improvement and is able to do so better than any human, then it may result in an intelligence explosion. This is an idea that I.J. Good was already worried about soon after this, and has since become one of the concerns that people have about artificial intelligence. But at this time, Turing is just trying to point out, this is a thing you can think about, a machine thinking about itself, if it thinks about anything. So now, the criticism that a machine cannot have much diversity of behavior is just a way of saying that it cannot have much storage capacity. And until fairly recently, a storage capacity of even 1,000 digits was very rare. Remember, this is basically 3 kilobits. That is tiny by modern standards, but up until a few years before 1950, it was difficult to come by. The machines that broke the German codes were just infinitesimal fractions of the machines that we have now. The criticisms that we're considering here are often disguised forms of the argument from consciousness. Usually, if one maintains that a machine can do one of these things and describes the kind of method the machine could use, one will not make much of an impression. It is thought that the method, whatever it may be, for it must be mechanical, is really rather base. Compare the parenthesis in Jefferson's statement, quoted on page 21. So let's go back. Yes, no mechanism could feel and not merely artificially signal in an easy contrivance. That is, it's easy to just dismiss these things as contrivances if you haven't actually seen it in operation. Objection 6, Lady Lovelace's objection. Our most detailed information of Babbage's analytical engine comes from a memoir by Lady Lovelace. Ada Lovelace was the daughter of Lord Byron, and she's often thought of as the founder of computer programming because she worked out the theoretical possibilities of how you would instruct an analytical engine to do things. In this memoir, she states, "The analytical engine has no pretensions to originate anything. It can do whatever we know how to order it to perform," her italics. This statement is quoted by Hartree, who adds, "This does not imply that it may not be possible to construct electronic equipment which will think for itself, or in which, in biological terms, one could set up a conditioned reflex, which would serve as a basis for learning. Whether this is possible in principle or not is a stimulating and exciting question, suggested by some of these recent developments. But it did not seem that the machines constructed or projected at the time had this property." This is an important point that is central to much of later artificial intelligence. I'm in thorough agreement with Hartree over this. It will be noticed that he does not assert that the machines in question had not got the property, but rather that the evidence available to Lady Lovelace did not encourage her to believe that they had it. It is quite possible that the machines in question had, in a sense, got this property, that is, the property of being able to learn from experience and do new things. For suppose that some discrete state machine has this property. The analytical engine was a universal digital computer, so that if its storage capacity and speed were adequate, it could, by suitable programming, be made to mimic the machine in question. Probably this argument did not occur to the Countess or to Babbage. In any case, there was no obligation on them to claim all that could be claimed. But this whole question will be considered again under the heading of learning machines. A variant of Lady Lovelace's objection states that a machine can never do anything really new. This may be parried for a moment with the saw. There is nothing new under the sun. Who can be certain that original work that he has done was not simply the growth of the seed planted in him by teaching, or by the effect of following well-known general principles? So this is an important point to say. What does it mean for something to be new? Can humans do new things? Some people might object. But anyway, he says, a better variant of the objection says that a machine can never take us by surprise. This statement is a more direct challenge and can be met directly. Machines take me by surprise with great frequency. This is largely because I do not do sufficient calculation to decide what to expect them to do, or rather because, although I do a calculation, I do it in a hurried, slipshod fashion, taking risks. Perhaps I say to myself, I suppose the voltage here ought to be the same as there. Anyway, let's assume it is. Naturally, I'm often wrong, and the result is a surprise for me by the time the experiment is by the time the experiment is done, these assumptions have been forgotten. These admissions lay me open to lectures on the subject of my vicious ways, but do not throw any doubt on my credibility when I testify to the surprises I experience. If you have ever done any computer programming, you will also agree. You think that you've written the program to do exactly what it's supposed to do, and then something surprising happens. It crashes. Why is that? Oh, because I forgot this step had to do that. Yeah, the machine surprises you all the time because it's doing exactly what it was told to do, and you didn't think about what exactly that meant. He says, I do not expect this reply to silence my critic. He will probably say that such surprises are due to some creative mental act on my part and reflect no credit on the machine. This leads us back to the argument from consciousness and far from the idea of surprise. It is a line of argument we must consider closed, but it is perhaps worth remarking that the appreciation of something as surprising requires as much of a creative mental act, whether the surprising event originates from a man, a book, or a machine, or anything else. The view that machines cannot give rise to surprises is due, I believe, to a fallacy to which philosophers and mathematicians are particularly subject. This is the assumption that as soon as a fact is presented to a mind, all consequences of that fact spring into the mind simultaneously with it. This is sometimes described in philosophical literature as the problem of logical omniscience. Any way of describing a method of rational thought is going to suggest that if you believe something, then all the logical consequences of that thing are already things that you should believe. But that means, what's the point of mathematics? All of mathematics is working out the logical consequences of things we already knew. How is mathematics ever unknown or surprising? It's a very useful assumption under many circumstances, but one too easily forgets that it is false. A natural consequence of doing so is that one then assumes that there is no virtue in the mere working out of consequences from data and general principles. So I think his point here is, just because all of the output is already contained in the program doesn't mean there's nothing interesting, novel, creative, new in the output. Somehow the fact that the program contains that, and we didn't realize that, is indicative that there's something importantly new there. Section 7, argument from continuity in the nervous system. This is where he's going to talk about neural networks. The nervous system is certainly not a discrete state machine. A small error in the information about the size of a nervous impulse impinging on a neuron may make a large difference to the size of the outgoing impulse. It may be argued that, this being so, one cannot expect to be able to mimic the behavior of the nervous system with a discrete state system. It is true that a discrete state machine must be different from a continuous machine. But if we adhere to the conditions of the imitation game, the interrogator will not be able to take any advantage of this difference. The situation can be made clearer if we consider some other, simpler continuous machine. A differential analyzer will do very well. A differential analyzer is a certain kind of machine, not of the discrete state type, used for some kinds of calculation. I think it's something where you can like trace out a curve and it'll calculate the area that you traced. Some of these provide their answers in a typed form, and so they are suitable for taking part in the game. It would not be possible for a digital computer to predict exactly what answers the differential analyzer would give to a problem, but it would be quite capable of giving the right sort of answer. For example, if asked to give the value of pi, actually about 3.1416, it would be reasonable to choose at random between the values 3.12, 3.13, 3.14, 3.15, 3.16, with the probabilities of 0.05, 0.15, 0.55, 0.19, 0.06, for instance. Under these circumstances, it would be very difficult for the interrogator to distinguish the differential analyzer from the digital computer. And I'll just say a little bit more. The modern artificial intelligence devices that are most common are based on neural net architecture. They're imitating the way that the nervous system works. Interestingly, most of them do so on a digital computer, where they just have a digital representation of the activation of neurons. And these tiny differences in the activation of neurons can make a big difference. They do it digitally, so on some level, it's not the same as a continuous thing. But it's close enough that you can't really tell the difference in the output. And importantly, they're also developing new machines that will do this in a continuous way on the fundamental level, because they're thinking this might enable faster neural networks. But Turing's point is, in the imitation game, you can't really tell the difference between these things. And so it doesn't seem relevant to the question of whether it's really thinking, at least not in a sense that matters to us. Objection 8, the argument from informality of behavior. It is not possible to produce a set of rules purporting to describe what a man should do in every conceivable set of circumstances. One might, for instance, have a rule that one is to stop when one sees a red traffic light and to go if one sees a green one. But what if, by some fault, both appear together? One may perhaps decide that it's safest to stop, but some further difficulty may well arise from this decision later. To attempt to provide rules of conduct to cover every eventuality, even those arising from traffic lights, appears to be impossible. With all this, I agree. That is, his point is, if you look at the actual traffic laws, you'll notice actual humans on the road don't behave in accordance with those traffic laws. They diverge from them in many ways, in part because there are many situations that the traffic laws don't really consider. And people make decisions about this all the time, and they haven't consciously thought about and planned the rules for all this. Some people want to say, this means there therefore couldn't be any rules that describe all this. So he says, from this it is argued that we cannot be machines. I shall try to reproduce the argument, but I fear I shall hardly do it justice. It seems to run something like this. If each man had a definite set of rules of conduct by which he regulated his life, he would be no better than a machine. But there are no such rules, so men cannot be machines. The undistributed middle is glaring. I think here he's saying, well, what makes you think there are no such rules? And if there were such rules, they'd be no better than a machine. But even if there aren't rules, why does that mean you're better than a machine? All we've said is that if there were rules, you would be like a machine. Without rules, how do we know you're not also like a machine? I do not think the argument is ever put quite like this, but I believe this is the argument used nevertheless. There may, however, be a certain confusion between rules of conduct and laws of behavior to cloud the issue. By rules of conduct, I mean precepts such as stop if you see red lights, on which one can act and of which one can be conscious. By laws of behavior, I mean laws of nature as applied to a man's body, such as if you pinch him, he will squeak. Most people don't intentionally plan to have that rule, but they follow it nonetheless. If we substitute laws of behavior which regulate his life for laws of conduct by which he regulates his life, in the argument quoted, the undistributed middle is no longer insuperable. For we believe that it is not only true that being regulated by laws of behavior implies being being some sort of machine, though not necessarily a discrete state machine, but conversely, that being such a machine implies being regulated by such laws. However, we cannot so easily convince ourselves of the absence of complete laws of behavior as of complete rules of conduct. This is the entire idea of psychology. We're interested in understanding how do people work? Not how do people think they work, but how do people actually work? You don't know the rules by which you work, but maybe there are rules. The only way we know of for finding such laws is scientific observation. And we certainly know of no circumstances under which we could say, we've searched enough, there are no such rules. We can demonstrate more forcibly that any such statement would be unjustified. For suppose that we could be sure of finding such laws if they existed. Then, given a discrete state machine, it should certainly be possible to discover by observation sufficient about it to predict its future behavior, and this within a reasonable time, say 1,000 years. But this does not seem to be the case. I've set up on the Manchester computer a small program using only 1,000 units of storage, whereby the machine supplied with one 16-figure number replies with another within 2 seconds. I would defy anyone to learn from these replies sufficient about the program to be able to predict any replies to untried values. I think this is really the central response to these objections about creativity. Mathematics is just so complicated that you can write down a very simple equation that'll take a 16-digit number and report a 16-digit number. And if you just check a whole bunch of instances, that'll not be enough to figure out how is the machine going to behave on the next 16-digit number. Even if I gave you 1,000 years, you'd only be able to try a few million different numbers. But there are, trillions or quadrillions of 16-digit numbers? And so you'd never be able to test even more than a tiny fraction of the possible outputs if you were just getting one per second. And so very simple equations can lead to complex and unpredictable behavior just because the number of possibilities is so vast. And so just because we've seen humans and seen them behave and not ever seen very simple patterns of repeat doesn't mean that there isn't some rule that is relatively simple that's behind the scenes. It just means we haven't found it yet. Objection 9, the argument from extrasensory perception. This one seems a little bit surprising to a modern audience. I assume that the reader is familiar with the idea of extrasensory perception and the meaning of the 4 items of it, that is, telepathy, clairvoyance, precognition, and psychokinesis. That is, the ability to feel things from a distance, to see things from a distance, to sense the future, and to move things with your mind. These disturbing phenomena seem to deny all our usual scientific ideas, how we should like to discredit them. Unfortunately, the statistical evidence, at least for telepathy, is overwhelming. I think this is not true. I think he was probably misled by a little bit of statistical evidence that was arriving in the late 1940s, but it's still interesting to consider. It is very difficult to rearrange one's ideas so as to fit these new facts in. Once one has accepted them, it does not seem a very big step to believe in ghosts and bogies. The idea that our bodies move simply according to the known laws of physics, together with some others not yet discovered but somewhat similar, would be one of the first to go. The argument is, to my mind, quite a strong one. One can say in reply that many scientific theories seem to remain workable in practice in spite of clashing with ESP, that in fact one can get along very nicely if one forgets about it. This is rather cold comfort, and one fears that thinking is just the kind of phenomenon where ESP may be especially relevant. A more specific argument based on ESP might run as follows. Let us play the imitation game, using as witnesses a man who is good as a telepathic receiver and a digital computer. The interrogator can ask such questions as, what suit does the card in my right hand belong to? The man, by telepathy or clairvoyance, gives the right answer 130 times out of 400, while the machine can only guess at random and perhaps gets 104 right. So the interrogator makes the right identification. Now, he says, there is an interesting possibility which opens here. Suppose the digital computer contains a random number generator. Then it will be natural to use this to decide what answer to give. But then the random number generator will be subject to the psychokinetic powers of the interrogator. Perhaps this psychokinesis might cause the machine to guess right more often than would be expected on a probability calculation, so that the interrogator might still be unable to make the right identification. On the other hand, he might be able to guess right without any questioning, by clairvoyance. With ESP, anything may happen. If telepathy is admitted, it will be necessary to tighten our test up. The situation could be regarded as analogous to that which would occur if the interrogator were talking to himself and one of the competitors was listening with his ear to the wall. To put the competitors into a telepathy-proof room would satisfy all requirements. So that's an interesting point. The only objection that Turing really considers a strong one to the Turing test is the one that maybe ESP is possible and humans can do it and the machines can't. But he's also thinking maybe machines could do it too. And if so, that would erase that difference. Okay, so now section 7, learning machines. The reader will have anticipated that I have no very convincing arguments of a positive nature to support my views. If I had, I should not have taken such pains to point out the fallacies and contrary views. But such evidence as I have, I shall now give. So let us return for a moment to Lady Lovelace's objection, which stated that the machine can only do what we tell it to do. One could say that a man can inject an idea into the machine and that it will respond to a certain extent and then drop into quiescence, like a piano string struck by a hammer. Another simile would be an atomic pile, that is like a nuclear bomb, of less than critical size. An injected idea is to correspond to a neutron entering the pile from without. Each such neutron will cause a certain disturbance which eventually dies away. If, however, the size of the pile is sufficiently increased, the disturbance caused by such an incoming neutron will very likely go on and on increasing until the whole pile is destroyed. Is there a corresponding phenomenon for minds? And is there one for machines? There does seem to be one for the human mind. The majority of them seem to be subcritical, i.e. to correspond in this analogy to piles of subcritical size. I think this is a very speculative part of the paper. He's saying, an idea presented to such a mind will on average give rise to less than one idea in reply. A smallish proportion are supercritical. That is, he's saying there are some people who are such that if you give them a new idea, they'll think about it, they'll come up with a little bit more, but that's all they'll do. But he says some people are supercritical. Their mind contains so much complexity that if you give them an idea, then the resonances of that idea will grow, and they'll eventually come up with more new stuff. An idea presented to such a mind may give rise to a whole theory consisting of secondary, tertiary, and more remote ideas. Animal minds seem to be very definitely subcritical. Adhering to this analogy, we ask, can a machine be made to be supercritical? The skin of an onion analogy is also helpful. In considering the functions of the mind or the brain, we find certain operations which we can explain in purely mechanical terms. So things like certain amounts of visual processing, that the light hits the retina and the nerve is excited, and this hits the next nerve cell and does something. We might say this does not correspond to the real mind. It's a sort of skin which we must strip off if we're to find the real mind. But then in what remains, we find a further skin to be stripped off, and so on. Proceeding in this way, do we ever come to the real mind? Or do we eventually come to the skin which has nothing in it? In the latter case, the whole mind is mechanical. It would not be a discrete state machine, however, we've discussed this, because it's got these neurons which are continuous. The last two paragraphs do not claim to be convincing arguments. They should rather be described as recitations tending to produce belief. The only really satisfactory support that can be given for the view expressed at the beginning of section 6, that is the view that machines can think, that is, they can eventually pass the imitation game, will be that provided by waiting for the end of the century and then doing the experiment described. We've waited for the end of the century. We've seen that the machines didn't quite pass the test then, but now they're doing a much better job. What can we say in the meantime? What steps should be taken now if the experiment is to be successful? As I have explained, the problem is mainly one of programming. Advances in engineering will have to be made too, but it seems likely that these will not be adequate for the It seems unlikely that these will not be adequate for the requirements. Estimates of the storage capacity of the brain vary from 10 to the 10th to 10 to the 15th binary digits. I think these days people are thinking a larger number, but still, 10 to the 12th is, I believe, terabyte, 10 to the 15th is a petabyte. There are machines that are doing those things. I incline to the lower values and believe that only a very small fraction is used for the higher types of thinking. Most of it is probably used for the retention of visual impressions. That is, he thinks most of our brain is just dedicated to representing visual imagery and not to real thought, which is an interesting question about why he's distinguishing that too. I should be surprised if more than 10 to the 9th was required for satisfactory playing of the imitation game, at any rate against a blind man. Note, the capacity of the Encyclopedia Britannica 11th edition is 2 times 10 to the 9th. That is, it's 2 gigabits. I think Wikipedia is now like 60 gigabytes, so it's about 100 times bigger than the Encyclopedia Britannica, but still totally manageable on a computer. A storage capacity of 10 to the 7th, that is 10 megabits, which is about 3 megabytes, would be a very practicable possibility even by present techniques. It's probably not necessary to increase the speed of operation of the machines at all. Now that's an interesting point. Machines have gotten a lot faster. Parts of modern machines which can be regarded as analogs of nerve cells work about 1,000 times faster than the latter. This should provide a margin of safety which could cover losses of speed arising in many ways. Our problem then is to find out how to program these machines to play the game. At my present rate of working, I produce about 1,000 digits of program a day, so that about 60 workers working steadily through the 50 years might accomplish the job if nothing went into the waste paper basket. Some more expeditious method seems desirable. And that's interesting. That's one of a long history of people being over enthusiastic about artificial intelligence. It took much more than 60 people working for 50 years to come up with the kinds of learning algorithms that we have today. But Turing already had the important idea, which is coming in these next paragraphs. In the process of trying to imitate an adult human mind, we're bound to think a good deal about the process which has brought it to the state that it is in. We may notice 3 components: the initial state of the mind, say at birth, the education to which it has been subjected, other experience, not to be described as education, to which it has been subjected. Instead of trying to produce a program to simulate the adult mind, why not rather try to produce one which simulates the child's? If this were then subjected to an appropriate course of education, one would obtain the adult brain. And this is a really important idea. All of the modern artificial intelligence programs are done by creating a general learning algorithm and then just giving it vast amounts of data. He says, presumably the child brain is something like a notebook as one buys it from the stationers. Rather little mechanism and lots of blank sheets. Mechanism and writing are, from our point of view, almost synonymous. One hopes that there is so little mechanism in the child brain that something like it can be easily programmed. The amount of work in the education we can assume as a first approximation to be much the same as for the human child. Now here he's been taking a very distinct line on how the mind works. This is what they call the empiricist tradition, on which the mind is like a blank slate and there's very little in it at birth, and it's all experience that gives us our adult capacities. And at around the same time, Noam Chomsky was working on exactly the opposite idea, and much of modern cognitive science is based on the opposite idea, that actually the mind has a huge amount of innate machinery, and this is often said to be the rationalist idea, that there's lots of innate knowledge, which we then trigger with small amounts of information from the outside world in order to develop our adult capacities. And Chomsky argues that the amount of language that a child is exposed to before the age of 5 is not nearly enough to learn language. Now, modern artificial intelligence neural networks do have something like simple mechanisms. They're validating something more like the empiricist program, but they're given huge amounts of data, much more than human children are. And it's an interesting question to see how much more needs to be built into the machines in order to bring down the amount of data that's needed. So we've thus divided our problem into two parts, the child program and the education process. These two remain very closely connected. We cannot expect to find a good child machine at the first attempt. One must experiment with teaching one such machine and see how well it learns. One can then try another and see if it's better or worse. There's an obvious connection between this process and evolution by the identifications. Structure of the child machine equals hereditary material. Notice this is 1950. They didn't know it was DNA yet. They just knew there were genes. Changes equal mutations. Natural selection equals judgment of the experimenter. One may hope, however, that this process will be more expeditious than evolution. This is an idea that people later in the 20th century call genetic algorithms, where you just randomly perturb the program in various ways, decide which is doing better, and then work with that one. The survival of the fittest is a slow method for measuring advantages. The experimenter, by the exercise of intelligence, should be able to speed it up. Equally important is the fact that he is not restricted to random mutations. If he can trace a cause for some weakness, he can probably think of the kind of mutation which will improve it. It will not be possible to apply exactly the same teaching process to the machine as to a normal child. It will not, for instance, be provided with legs so that it could not be asked to go out and fill the coal scuttle. If you're anything like most people who were born after this paper was written, you were probably not asked to go fill the coal scuttle as a child either. Our educational experiences as children are now very different from what they were before the 1950s. Possibly it might not have eyes. But however well these deficiencies might be overcome by clever engineering, one could not send the creature to school without the other children making excessive fun of it. It must be given some tuition. We need not be too concerned about the legs, eyes, etc. The example of Miss Helen Keller shows that education can take place, provided that communication in both directions between teacher and pupil can take place by some means or other. And I'll link a video in the description below of Helen Keller as an adult, so you can see how someone without sight or hearing was able to learn. We normally associate punishments and rewards with the teaching process. Some simple child machines can be constructed or programmed on this sort of principle. The machine has to be so constructed that events which shortly preceded the occurrence of a punishment signal are unlikely to be repeated, whereas a reward signal increased the probability of repetition of the events which led up to it. These definitions do not presuppose any feelings on the part of the machine. I've done some experiments with one such child machine and succeeded in teaching it a few things, but the teaching method was too unorthodox for the experiment to be considered really successful. So here he's taking ideas that were really important in psychology in the early 20th century. The psychologist B.F. Skinner had this method of training rats and pigeons, where he showed that Certain kinds of behavior, if you give them a sweet treat afterwards, they'll do it more often. And if you give them an electrical shock, they'll do it less often. And Turing realized all that matters is this formal property that if you do the one thing, it happens more often. If you do the other thing, it happens less often. And so he just wrote a program where the behavior was always random, but if it got a reward for doing something, then it would do more of that thing. And if it got a punishment for doing something, it would do less of that thing. Reward and punishment are just signals that increase or decrease the probability. And so if you learn the appropriate rewards and punishments, you can train the machine. And something like this sort of reinforcement learning is actually at the groundwork of all modern neural networks. The use of punishments and rewards can at best be a part of the teaching process. Roughly speaking, if the teacher has no other means of communicating to the pupil, the amount of information which can reach him does not exceed the total number of rewards and punishments applied. By the time a child has learned to repeat Casabianca, he would probably feel very sore indeed if the text could only be discovered by a 20 questions technique, every no taking the form of a blow. So yeah, if you're trying to teach someone a whole poem and all you can tell them is you hit them and say, go back to the beginning every time they get a word wrong, and then you say nice things every time they get a word right, it'll take them forever to learn a poem. Whereas if you could tell them the words and then use the reinforcement on top of that, it would go much faster. It is necessary, therefore, to have some other unemotional channels of communication. If these are available, it is possible to teach a machine by punishments and rewards to obey orders given in some language, e.g. a symbolic language. These orders are to be transmitted through the unemotional channels. The use of this language will diminish greatly the number of punishments and rewards required. And think about how it works when you're training a dog. That maybe at first you have to give the dog a treat every single time it does something that you associate with the clicker. But then at a certain point, it starts to notice, the clicker is already the reward, and so you can train it much faster. Opinions may vary as to the complexity which is suitable in the child machine. One might try to make it as simple as possible, consistently with the general principles. Alternatively, one might have a complete system of logical inference built in, or rather programmed in, for our child machine will be programmed in a digital computer, but the logical system will not have to be learned. In the latter case, the store would be largely occupied with definitions and propositions. The propositions would have various kinds of states, e.g. well-established facts, conjectures, mathematically proved theorems, statements given by an authority, expressions having the logical form of proposition but not belief value. Certain propositions may be described as imperatives. The machine should be constructed so that as soon as an imperative is classed as well-established, the appropriate action automatically takes place. To illustrate this, suppose the teacher says to the machine, do your homework now. This may cause teacher says do your homework now to be included among the well-established facts. Another such fact might be everything the teacher says is true. Combining these might eventually lead to the imperative do your homework now being included amongst the well-established facts. And this, by the construction of the machine, will mean that the homework actually gets started. But the effect is very satisfactory. The processes of inference used by the machine need not be such as would satisfy the most exacting logicians. There might, for instance, be no hierarchy of types. That's an issue in logic from the early 20th century. But this need not mean that type fallacies will occur any more than we are bound to fall over unfenced cliffs. Suitable imperatives expressed within the systems, not forming part of the rules of the system, such as do not use a class unless it is a subclass of one which has been mentioned by teacher, can have a similar effect to do not go too near the edge. So much of the details of the second half of that paragraph are relevant to people who know a lot about early 20th century logic, but I think the first half of that paragraph is the most important, that you might start with basically just a blank network that is trained by reinforcement learning, or you might start with a huge database that you then train by reinforcement learning how to use. Interestingly, the modern neural networks like ChatGPT are all much more like the former. They don't actually have any sort of logical inference or any sort of database in them. They just have a learning system and they've read through everything many times, but they don't memorize it. They just learn and develop patterns of behavior. And that's why they end up being so bad at logic in many cases. But they still turn out to be remarkably amazing at many other things. The imperatives that can be obeyed by a machine that has no limbs are bound to be of a rather intellectual character, as in the example doing homework given above. Important amongst such imperatives will be ones which regulate the order in which the rules of the logical system concerned are to be applied. For at each stage, when one is using a logical system, there is a very large number of alternative steps, any of which one is permitted to apply, so far as obedience to the rules of the logical system is concerned. These choices make the difference between a brilliant and a footling reasoner, not the difference between a sound and a fallacious one. For an analogy, think about someone who's playing the game of chess. If you know the rules of chess, you already know every move that is possible. But the interesting question is, which rules should I do? Which rules are good ones to follow at the moment? And anyone who knows the rules can play chess, but you have to have some interesting idea of how to decide which ones to apply in order to do it well. And he's pointing out that this is a general problem for reasoning. And so he says propositions leading to imperatives of this kind might be, when Socrates is mentioned, use the syllogism in Barbara. That'll make sense if you know medieval logic. Or if one method has been proved to be quicker than another, do not use the slower method. Some of these might be given by authority, but others might be produced by the machine itself, e.g. by scientific induction. And this is the interesting thing. This is how chess programs and Go programs work. They know the rules of the game from the beginning, but what they learn from doing lots and lots of plays is, what are good heuristics to figure out which rules should I apply right now? Which moves are good ones? The idea of a learning machine may appear paradoxical to some readers. How can the rules of operation of the machine change? They should describe completely how the machine will react, whatever its history might be, whatever changes it might undergo. The rules are thus quite time invariant. This is quite true. The explanation of the paradox is that the rules which get changed in the learning process are of a rather less pretentious kind, claiming only an ephemeral validity. The reader may draw a parallel with the Constitution of the United States. That is, the Constitution has a process of amendment. There are certain parts of the Constitution that are not allowed to be amended, and then the other parts can be amended, and those are much harder to change still than the ordinary rules and laws that govern ordinary behavior. And these machines can do the same thing. They can have a basic outline that structures how they work, that makes them a universal machine, but then they can edit their own programming in ways that make them better. An important feature of a learning machine is that its teacher will often be very largely ignorant of quite what is going on inside, although he may still be able to some extent to predict his pupil's behavior. This should apply most strongly to the later education of a machine arising from a child machine of well-tried design or program. This is an important point that has been essential to understand about modern neural networks. The people who make them don't understand how they work. They understand how they learn, and then they understand the data that's been given, but they don't understand what the machine is now learned to do on the basis of that data. This is in clear contrast with normal procedure when using a machine to do computations. One's object is then to have a clear mental picture of the state of the machine at each moment in the computation. This object, having this clear picture of the state of the machine, can only be achieved with a struggle. The view that the machine can only do what we know how to order it do, as Lady Lovelace said, appears strange in the face of this. Most of the programs which we can put into the machine will result in its doing something that we cannot make sense of at all, or which we regard as completely random behavior. Intelligent behavior presumably consists in a departure from the completely disciplined behavior involved in computation, but a rather slight one, which does not give rise to random behavior or to pointless repetitive loops. Another important result of preparing our machine for its part in the imitation game by a process of teaching and learning is that human fallibility is likely to be omitted in a rather natural way, i.e. without special coaching. The reader should reconcile this with the point of view on pages 24 and 25. Processes that are learned do not produce 100% certainty of result. If they did, they could not be unlearned. That's an important point. it is probably wise to include a random element in a learning machine. A random element is rather useful when we're searching for a solution of some problem. Suppose, for instance, we wanted to find a number between 50 and 200, which was equal to the square of the sum of its digits. We might start at 51, then try 52, and go on until we got a number that worked. Alternatively, we might choose numbers at random until we got a good one. This method has the advantage that it's unnecessary to keep track of the values that have been tried, but the disadvantage that one might try the same one twice. But this is not very important if there are several solutions. The systematic method has the disadvantage that there may be an enormous block without any solutions in the region which has to be investigated first. Now, the learning process may be regarded as a search for a form of behavior which will satisfy the teacher or some other criterion. Since there's probably a large number of satisfactory solutions, the random method seems to be better than the systematic. That is, if we're imagining what the child is trying to do is learn how to satisfy the teacher, as opposed to learn how to think the same way the teacher does, then it's good if the child just sort of tries things at random until it eventually finds some way of satisfying the teacher. And what it stumbles upon may be quite different from what someone else did. It should be noticed that this is used in the analogous process of evolution. But there, the systematic method is not possible. How could one keep track of the different genetic combinations that had been tried so as to avoid trying them again? We may hope that machines will eventually compete with men in all purely intellectual fields. But which are the best ones to start with? Even this is a difficult decision. Many people think that a very abstract activity, like the playing of chess, would be best. It can also be maintained that it is best to provide the machine with the best sense organs that money can buy, and then teach it to understand and speak English. This process could then follow the normal teaching of a child. Things would be pointed out and named, etc. Again, I do not know what the right answer is, but I think both approaches should be tried. We can only see a short distance ahead, but we can see plenty there that needs to be done. And I think this ending is so amazing. He's pointing out that there are two things that you might try to do. You might try to program the information, or you might try to teach it to learn it. You might try to work symbolically. You might try to work with a neural network. You might try to just use the symbolic code, or you might try to give it robotic interactions with the world. And all of these things have been very important in the development of artificial intelligence since his time. Artificial intelligences didn't get satisfactory passing of the Turing test by the time he thought, but they have done much better in many ways than many people would have expected. And it's interesting to note that he has all of this in 1950. And also remember to note that when he talks about the Turing test, he's not just talking about, can you convince someone for 5 minutes that this is a human? He's asking, can you convince someone in all the ways that matter to being a friend with them that this is an intelligent and worthy companion? And that's the real Turing test.